I wanted to say a couple of things about amenable groups before I start my proper lecture today to kind of tie up what I was saying last time. So supposing we have a discrete countable with suitable definition of entropy, you can prove the same theorems as I was talking about yesterday, which was just for the case of Z, for any discrete countable amenable group. So, for example, take a fullness take a partition P, then you can take equal the join over G and F. That gives you one of these partitions like I was talking about yesterday. You can define H of P F to be 1 over F, number of elements of F. You can define H of P G, if G is an amenable group acting on the partition, to be limit as n goes to infinity H of P F. Or maybe I'll write n, where this limit is taken over a Fellner sequence, and it's independent of the Fellner sequence. And you can define H of G equal to the supremum over P finite partitions so these are all the exact obvious generalizations of the notions I was talking about yesterday. You can define so all these are the same. Thank you, I will. And after 50 minutes, I'm going to start writing larger again. So these are all the exact analogues of the definitions I was talking about yesterday, which you would make once you had a Fellner sequence instead of just Z. And then in 1987, Ornstein and Weiss showed that They're isomorphic if and only if they have the same entropy. So in other words, the major theorem I talked about last time, Ornstein's theorem, actually holds for discrete, countable, amenable groups. And I've kind of said, look, it's obvious you just do this, this, and this, but there's a lot of work that goes into actually proving this theorem for discrete, countable, amenable groups. Now I want to kind of link this with what I'm about to say today. I haven't defined yet what an amenable equivalence relation is. But you'll know that in a little while. Yes. Do I need, I probably don't need, no. Of course, if I equals j, then, yeah. So it follows from this that the action of an amenable group is orbit equivalent, and I don't think I've told you what orbit equivalence is. But that's the first step in my today's lecture, which I haven't started yet. To an action of Z. And in fact, Rudolph and Weiss in 2000 showed that the action of G have the same entropy. So for orbit equivalence, which is a coarser type of equivalence than metric isomorphism, then amenable group actions and Z actions are the same thing. So that's a kind of statement I would have liked to make at the end last time, because it would have whetted your appetite for a discussion of orbit equivalence, which I'm about to start now. So that's if I'd gone 5 minutes over yesterday, that's what I would have said in that 5 minutes. And that kind of completes my sort of statements about... by the way, Sri Hari and his team have photocopied all these lecture notes, and they've now scanned them into a PDF, and it's going to appear, or maybe already has appeared, on the conference website. So I've omitted a lot of proofs and other things. You can catch up with those proofs. So now let's start something completely different. Do you like Monty Python? And now for something completely different. Well, not completely different maybe, but my major topic today is about non-singular This might be the next chapter. Was I up to 4 or 5? So when Sundari asked me to talk at this conference, she said she would like me to do something in the borderline between harmonic analysis and ergodic theory. Till now, I suppose I've been more on the ergodic theory side. This is how I, as a harmonic analyst, started working in this area. I got into non-singular ergodic theory through Rees products. So I'd like to kind of explain to you how that happened. So we'll return to Z for the moment. But I'll assume that mu composed T is only an equivalent measure to mu, so that is not equal to 1. In all the cases we've done today, pretty much this Radon-Nikodym derivative has been equal to 1. And so why don't I'll call that omega k of x. Sometimes, if I'm writing long sums, I don't want to necessarily write that all over again, so I'll sometimes call that omega kx is no longer equal to 1, always. Yes?
You define a Bernoulli partition there, but that's a property of a partition. How do you define a Bernoulli action?
That means an action which has a Bernoulli partition which generates the whole sigma algebra under the action of G, which was the definition I used yesterday. And so I'd like to define for you what orbit equivalence is. Let's take x, b, mu, t, and y, c, mu, s, non-singular. So phi is an invertible measurable function between bimeasurable, so phi and phi inverse are both measurable from x to y. So that means it's going to be, instead of if for all x and for all n, there exists an m which depends on n and x. So that phi of t to the nx is equal to s to the m of nx phi x. So this is saying that phi, in the case of metric equivalence, when n was equal to 1, then m was equal to n. But now we're just saying that phi, instead of intertwining these two things, it maps the orbits of t to the orbits of s. This is clearly a weaker kind of notion, but if we're interested in the long-term behavior of the system, maybe it's a reasonable thing to say the long-term behavior is how do the orbits go to the orbits. And so this is saying there's a correspondence between the orbits. let me just note that m of n tx is times m of 1x equals m of n plus 1x. I hope that's right. So m is a co-cycle actually, and the study of that co-cycle action is kind of interesting. Somehow the whole orbit equivalence is encapsulated by what that co-cycle is doing. Well, at the moment they're all integers, but no, I'm thinking of a single group action here all the time. Oh, I see. Yes, they could belong to. Yes, you're right. They could belong to different groups. So let me talk about the von Neumann. So this is maybe section 4. I've not had any section numbers till now. Let me not start on the third lecture to have section numbers. So sometime in the 1930s, von Neumann suggested that there was a classification of non-singular dynamical systems into the following types. So the type 1s are kind of boring. They're just finite or countable spaces. So the type 2s are types where there is an invariant, a G invariant probability measure. And we saw, if an amenable group acts on a compact metric space, for example, there's always an invariant measure hanging around. And this is the province of a large amount of measure-preserving ergodic theory that I have been talking about to date. And then type 2 infinity. Invariant with mu of x equal to infinity. So that's another type of measure-preserving ergodic theory where there is no probability measure, but where there is an invariant. And then there were type 3, which is the rest, and that's where there is no equivalent. Invariant measure. And it's fairly easy to show that if you have an ergodic system, it must be exactly one of these types and can't be two of them at the same time. And in fact, even more, so if a system is type something or other, then anything orbit equivalent to it is the same type. Let me give you some, and he gave some examples. The type 1 are quite easy, but let's look at some type 2 and 3 examples. So, well, let's take this string of all infinite sequences of zeros and ones, one-sided. Infinite product of the same space over and over again, 0, 1. Choose, and we'll let mu be a measure on that, which is the infinite product of mu i's, where mu I is a probability measure on 0 and 1. So mu I of 0 plus mu I of 1 equals 1. And I guess we'll have, for non-singularity, we want both the weights to be non-zero. And I want T to be the odometer. There's not space down here to write down what the odometer is. It's some canonical transformation. In fact, if you're driving your car around and it was in binary and the little thing that measures how many miles you've done was written from right to left, then you would have exactly the odometer. So what does the odometer do? It takes, if you start with a 0 and then anything, it changes it to a 1 and then the same thing. If you start with a 1 and then, or if you start with a whole bunch of 1s and then a 0, it will change, and then something will change all the 1s to 0s. It will change the 0 to a 1, and then it will leave unaffected that thing there. So that's called the odometer. It's beloved of ergodic theorists. It's a single transformation of x. And what it does is it changes finitely many coordinates here, and so you can easily see that. If neither of those weights for any of the measures is 1, then you have a quasi-invariant measure. And so, for example, if mu I of 0 equals mu I of 1 equals a half, then you get invariant. Case, a 2, 1. But he also said, let's let mu I of 0 equal 1 over 1 plus lambda mu I of 1 equal to lambda over 1 plus lambda, where lambda is some number between 0 and 1. And that's called a type. And we'll start calling these type 3 lambda in a little while. Now, given any of these systems, you can create a von Neumann algebra from them. I guess that's what von Neumann's motivation was, and created a lot of work in von Neumann algebras as well. I'm going to really ignore the type 2 infinity cases for today's lecture. I'm just really concentrating on the type 3, in fact. So I'm not sure how much I want to say about this. Remember, we had the Koopman representation of T on L2 of x mu. So that maps f onto f composed t to the n times the square root of omega n. And you can also multiply by L infinity functions. Those two operations together give you a fairly complicated set of operators on L infinity, and it becomes a von Neumann factor. That was something that von Neumann proved, and there is a correspondence between the type of the factor and the type of these dynamical systems. And so a lot of this ergodic theory then links with von Neumann algebras, and I'm going to say almost nothing more about von Neumann algebras, but I think I thought I should make that remark en passant, as it were. Oh, maybe I'll just say one remark, that the type of the von Neumann factor